In the name of Allah, thank you so much and welcome back to lecture number 6. As we discussed that this is the uh, last lecture of the what we can say the remote sensing products. We discussed before this the remote sensing data set or data, and now we are discussing the data formats and its visualization. So this is the last lecture in the glance of the remote sensing products. The next six lecture will be about the new glance, which is the basic analysis, starting from the data correction and the data correction. And its seven lecture would be the basic analysis. So these 6 and 7 lecture is coming under the glance of the basic analysis. And the last one, which is the best advanced analysis in its application, it will be about the processing of remote sensing data and transformations. And the last lecture 9 will be about the land cover classification. So this lecture is the last lecture, as we said, about the remote sensing products. And we discussed before this the remotely sensed data. Now, the remotely sensed data is sensed. So in this case, now we are having the data. We are discussing the data formats, how the data is organized, how the data is saved, and how the data can be visualized, the Earth observation data. So multiple things will be discussed in the this lecture, which is about data formats, the data levels, and the NASA data levels, the European Space Agency levels, and multiple stuff. Let's start with the first one, the data in metadata. Remote sensing data is usually contains two parts. So far, we have discussed the data, the actual measurement values from the sensor. We were discussing only the data that we are observing or sensing the data of the electromagnetic waves, which is bounced back from the surface or the land surface of the target. But actually, the data has another part also, which is called metadata. Metadata, simple definition, is the information about the data. So exactly the same thing is applies here. It is information needed to understand the data. What data has been sensed by the satellite, that data need to have some more information to understand. So we are capturing two types. The remote sensing data actually contains two parts. One of them is by itself the data, numerical values or matrices, and the second is metadata. What is metadata? Metadata includes the geopolitical or geolocation, sorry for geopolitical word, geolocations and timestamps. I mean, geolocation, they are measuring which part of the data is this, and it's timestamp when this data has been recorded. And in the acquisition mode, what is the acquisition mode? It is directly nadir, or it is from the side angle, or the what is the mode? I mean, here they are discussing the mode. These all the stuff are mentioned and associated in the metadata. In sensor parameters, what are the parameters of the sensor? Number of rows, columns, and bands, and quality information, and cloud coverage. All these things are associated in the metadata when we are capturing or sensing the data using the satellite. So one is data and the other is called metadata. Very important data, very important idea. Without metadata, mostly remotely sensed data is incomplete all the time because the user cannot correctly interpret the location, time, sensor setting, and quality. These are the important stuff we need to keep in mind about the data and its visualization. Now the second slide is discussing about the multi-band raster data sets. So far we have seen that the remotely sensed data is using the raster data in the grid form. So what is multi-band raster data set? A multi-band raster data can be imagined as a large filling cabinet. So this is the intuition we are understanding about the multi-band raster data set. So if we take this example of the multi-band data set, multi-band raster data set, so assume this cabinet has an a drawer, and each drawer has a single pixel, represent a single pixel with multiple values. In the multiple values is due to the multiple bands. So this is exactly the intuition behind the multi-band raster dataset in reality. And each drawer represents a one pixel, and inside that pixels there are multi-band band values. So this single value means that inside this value we have more values. Like in single drawer we have multiple more values. In the inside that pixels there are multiple band values. So like B1, B2, we have seen the multiple band before this, and this is the multi-band raster data set. For example, the band 1 represents the blue, band 2 represents the green, and band 3 represents the red, and 4 is near infrared. So the key idea, one pixel in multispectral images contains several numerical values, not only one. And the reason is why they are carrying multiple values, that is the multi-band or multiple band raster data set. Because in that data set we have multiple bands. So this is the exactly representations of how the multi-band data set, raster data set works with multiple band values. Storage of a remote sensing data set. So far we discussed the in the chapter of the Earth observation Earth observation platforms, we have seen that the satellite has two parts or two segments. One is this the space segment, and one is the ground segment. In the space segment, we are having the satellite by itself, its instrument downlink, and onboard storage. And we have a ground part or ground segment where we are having the team and station processing the data, receiving the data. So according to the storage of the remote sensing data, we have a temporary onboarding storage also. But in alongside that, here we are discussing the storage of a remote sensing data. In terms of imaging, remote sensing data usually comes in raster format. We know about this because it has some benefits. Like raster format means it is a regular grid of the rows in columns. Each matrix element is a pixel, and each pixel may contain one or more band values. Why each pixel may contain one or more? If it's multiple bands, so each pixel can contain multiple values due to the bands and the multiple wavelength. And geographical reference is usually attached. The geographical reference is attached to, so we will discussing the data formats later on, and that format is called GeoTIFF. So GeoTIFF is one of the format of the such kind of data. Okay, the simple line here is remote sensing images are not just pictures. Like we have discussed, we have seen in the instrument lecture, as per my remembrance, that there, no, in the fourth number lecture, we have discussed about the remotely sensed data, about certain types of sensors. No, exactly in the third chapter, in the Earth observation instrument, we have seen multiple types of sensor. One of the sensor was the imagery sensor or non-imagery sensor. So this is exactly the same. The remote sensing images are not just pictures, and they are exactly geo-referenced numerical matrices. This is the storage of a remote sensing data format, which is the raster format. And the reason why it is simpler in the grade of rows and columns format, and each matrix element is in a pixel format, is a pixel, and each pixel represent one or more than one band's values. It depends upon how many bands we have collected, and geographical reference is usually attached for understanding the where this data has been captured. We are discussing metadata storage. Metadata storage is data in a metadata may be stored in one single file on a separate file. So it depends upon the size of the data we are collecting. Both must be delivered together. It is important because the data cannot really make sense without the metadata. Because metadata is useful to quick for data selection. For example, instead of the downloading the hundreds of megabytes, the user can check metadata first to assess the cloud cover. I mean, how many cloud coverage is there, the quality, the acquisition data. Acquisition data is also really important for the trend analysis and for the change effect analysis or fast changing phenomena in sensor mode. So this is the metadata storage, and it is either will be stored in a single file or in multiple files. Both must be delivered together, because if we have a metadata, so metadata can give information about the data, but there is no existence there exactly data available. And if we have the data and there is no metadata information in metadata, which we are defining metadata as the data information about the data. So if you don't have the information about the data, I mean, where the satellite captured the data, what was the time step, what was the sensor mode, what is the acquisition mode, and all the setting and quality. So we may don't know about it if we don't have metadata. But if we have, so it means they are giving certain information about the data, and that really makes sense, and it's ready for the processing. In the data levels, we will discuss then how we are processing. But before the data levels, we are discussing some terminologies. It's important. One of them is data takes, and the other one is data stripes. Data take is a complete acquisition, in simple words, a continuous satellite acquisition, and data stripe is the portion of that acquisition received by the ground station. So let's dive more. A data take is a continuous acquisition of a data set from a satellite in the specific imaging mode. So here they have the condition of the continuous acquisition with a specific condition. For the Sentinel-2 case, it means the satellite continuously acquire a stripe of Earth while moving along its orbit. So we discussed orbit. Orbit is we are discussing in terms of it's a path of the orbit, the satellites in certain altitude, inclination, and position. So in the along the orbit, they are going the satellites, so they are taking a continuous acquisition. But what is exactly data stripe? A full data may be too long for one ground station to receive. As in the ground, we discussed that it can be received as in a single file or multiple files. So for complete data tech receiving for the ground station, it's difficult. For a pool data, it might be too long or for the one ground station to receive. Therefore, it can be divided into data stripes, one per receiving station. So they are sending this data into multiple receiving station as the visibility for the satellite. So later data stripes are merged before achieving archiving. So before to archive them or store them, so they are merging by both back as received in multiple stations. So as I said in the key idea, the data take is exactly the continuous satellite acquisition, and the data stripe is the portion of that acquisition received by a ground station. That is the whole idea. Now we are discussing granules and tiles. These are some more terms in the data formats and visualization. So granules is basically the sub images linked to the satellite sensor hardware and detector layout. You can call them that the granules are the more hardware relevant, or the tiles are more for software in hardware software use or for the user end. So granules are not for the user and tiles are for the user. This is a short differentiation. Granules are the sub images linked to the satellite sensor in a satellite sensor hardware in detector layout. And for Sentinel-2 case, about 25 kilometers across the track and about 23 kilometers along the track. And the average size is the granules 27 MB. So granules are mainly important for the ground segment processing, not for the final user. So the final user do not have any dealing with the granules. So in terms of understanding the remote sensing, we can assume that granules are linked to sensor hardware and the tiles are user-oriented georeference product. So with the tiles, the users or the final users are dealing. What are the tiles? Tiles are a square or ortho images in a predefined earth projection. So in simple term, if we say the tiles is exactly the mathematically corrected parts of the complete stripe or a single stripe, and it's that's why they call ortho images is a predefined earth projection. For Sentinel-2, tiles are usually 100 by 100 kilometers square, and UTM and WEGS 84 projection. So they have given in this projection of UTM in WGS 84. The size is the tiles of 100 by 100 meter square. So if we take the short idea of the granules in tiles, the granules are linked to the sensor hardware. As we said, this is the sub images linked to the satellite sensor, but tiles are user-oriented geo-reference product. So they are geo-reference data. It is for the fast processing and previewing for the end users. So tiles, you can assume that it is the more predefined version, or they call them the ortho images in a predefined earth projection part from the complete stripe. Before we discuss the data text and data stripe. So data stripe is a portion of the acquisition received by a ground station. But this portion, when we are receiving, it's not still like pre-processed, or they need some more mathematical work to define. For the end user, this style is, I mean, more mathematically predefined earth projection. So that's why it is called like geo-referenced product for the end user. And for granules are linked mostly to the sensor hardware. Now we are discussing tile partitions of earth surface. How this tile partitions of earth surface is working. In the Sentinel-2 cases, if we see the divides, Sentinel-2 divides earth surface to many predefined tiles. So this is like predefined tiles already for the Sentinel-2 cases. Like how the tiles looks, if in the visuals we see, this is the satellite paths in a complete acquisitions. They are showing in this square boxes are representing the tiles, and it's a predefined tiles for when we are taking an acquisition. So this is working as a reference. So in the previous slide, we discussed that this is the users oriented geo-reference product. So users are more dealing with this in terms of the granules, which is directly hardware oriented or sensors hardware oriented. So the tile partition of the earth surfaces in the Sentinel-2 case divides the earth surface into many predefined tiles. It is predefined when we are having the acquisitions. So the tile have the fixed geographic positions and the naming convention, certain types of naming convention like the UTM and WGS84 projection. The important idea about this tile partitions of the earth surface, regardless of the original satellite SWAT we already discussed, that is the stripe we are taking. Orthocratified data is distributed in UTM shaped tiles. So this is exactly orthocratified data is distributed in UTM shaped tiles. In the left side of these shapes, they are representing the squares as in a tile partitions predefined. This helps us the tile partition when we are having the acquisition to know the which part of the tile has been received or data stripe has been received. If we go back again in the data text and data stripe, so data stripe will be literally we know that this position has been received or this position is still remaining. So it is helping in this way. That's why the tile partition of the earth surface are predefined. And at the end, they said that's regardless of the original satellite SWAT. So this is regardless from that, because if we see in this right side picture, in this picture, the complete acquisition has been shown by the long rectangle, which is actually the continuous acquisitions of the picture of the acquisitions of the sense data, which is exactly the SWAT or the complete stripe or data set, data tech. So this is defined for the sake to understand of the data as a reference point for the user. Now we are discussing the data levels. So far we understand about multiple things, starting from the data, what is data in collected data, metadata, multiband raster data sets. We have an intuitions for the filling cabinet, large cap filling cabinet. Then we have seen the storage of the remote sensing data, and what is how we are restoring the remote sensing data. It is actually saving in the raster format, and it is a regular grade of rows in columns, and each matrix is each matrix element is a pixel, and each pixel may contains one or more band values. It depends upon the number of bands we have collected from the wavelength, and geographical reference is usually attached. We will discuss this geographically reference is usually attached in the formats, and it's called GeoTIFF. This is one of the specific format. This information is usually attached. And then we discuss what is metadata storage, is either is a single file or in multiple files, and they should be delivered together. If one of them is missing, it's irrelevant and it's useless. So the user can check in the metadata first with the cloud coverage, the timestamp, quality acquisition mode, and sensor modes, and multiple settings. Then we discuss data take and data stripe. We discuss the granules and tiles. In short term, the granules are the sensor hardware oriented, and tiles are the user georeference product. Then we have seen how the tile partitions of our service is working. Now we are discussing the data levels. Data levels is initially introduced by the NASA, which is the National Space Agency of America. National America Space Agency, exactly the same as this is the abbreviation of the NASA, introduced a level system from level 0 to level 4. Later the same it is adopted by the European Space Agency, ESA. So what this data of the levels are discussing. So starting from the NASA levels, it is starting from the 0 to level 4, but one has a 1A, 1B. So if we totally calculate, start from 0, 1, 2, 3, 4, 5, 6, because 1 is 2, and start from the 0. So that is totally 6 levels. Each level represent specific stuff. If you see the level 0 in the NASA data level formats, they say this is the raw in reconstructed instrument data. The instrument is exactly the sensor they are discussing. What is collected by the sensor in the raw form, in only you can say reconstructed from the electromagnetic wave, that is level 1. Then the level 1A is discussing unprocessed data with time and ancillary information. Ancillary information and unprocessed data exactly the same. They are associating this information. Data is still unprocessed, but with the time in ancillary information. Ancillary information is the same. They are giving some more metadata about the data. In the level 1B, the data processed to sensor unit. Now the data has been processed to sensor units more, or processed. Now this is coming out of the sensor now. In the level 2, they are deriving the geophysical variables now. Geophysical multiple variables, like I said to you, in the metadata or ancillary, we have already attached in the level 1A, but in the level 2, they are basically attaching the geophysical variables for what we are actually looking for, the timestamps, the sensor mode. All these things actually are coming in the metadata as a part to understand about the data. But here actually on the ground, what we are looking for, those variables are attached in terms of multiple stuff we will discuss later on. That exactly what derived by the in geophysical variables in the level 2. In the level 3, variables map to uniform space time grids. Now this is mapping exactly to a single space of a time grid. They are saying, okay, this data acquisition has been taken from this time to this time. And in the level 4, the model output or analysis result. Then this is the level 4 data, which is the output or the analysis result, what we are looking for. And now it's ready for the final user. So it's in the usable format. The same data levels has been adopted by the European Space Agency also for the Sentinel-2. In the Sentinel-2 data levels, this is the important levels, but they are a little bit differentiating from them. That was starting from the level 0, and then level 1A, level 1 B, level 2, level 3, level 4, and divided in multiple. But the European Space Agency for the Sentinel-2, they are using starting from level 1, level 0, level 1 A, B, C, and level 2. So the level 1 is exactly the compressed raw images data. This is more compressed, whatever this is collected by the sensor from the uh, mm, electromagnetic waves bounce back. In the level 1A, it is a decompressed saturated level 1 data. Now we are decompressing the data in the level 1A, which is actually coming from the level 10. Then in the level 1B, radiometrically corrected imagery in the top of atmospheric radiance sensor geometry. We have two important concepts, TOA, top of atmospheric, and bottom of atmosphere. The radiometrically corrected imagery means that those signals which are bounced back or gone accurately from the atmosphere and it has been captured by the sensor, it means this is the top of the atmosphere. Now discussing that area, that radiance. So this is corrected imagery in sensor geometry. So sensor correctedly, this is the level 1B. In this level 1 of the data levels, we are correcting that radiometrically. And the radiometrically mainly discuss that the strength of the signal depends upon the intensity in the radiance. So if the intensity in the radiance is good, so radiometrically corrected already, then they don't need more correction. But if it's not, so they need to be corrected. So this level is totally coming on the top of the atmosphere. That's why they called in the level 1B radiometrically corrected imagery is in the top of the atmosphere radiance and sensor geometry. In the level 1C, the top of atmospheric reflectance, as we discussed throughout the course multiple times, they actually we are collecting the radiance and along the radiance, or we can say intensity, so of the electromagnetic waves. It is not exactly the reflectance. The reflectance is derived after certain processing. So in the level 1C of the top atmosphere, top of atmosphere, reflectance is derived from the radiance in tiled products. We have seen the tiled products, so this information is now derived in the level 1C of the reflectance in the level 1. Sorry, now we have completed the level 0 and level 1, 3 level A, B, C. Now we are in the level 2, which is the bottom of atmosphere reflectance after atmospheric correction. Now we have correctedly the atmospheric corrections after the reflectance of the bottom atmosphere. So in this level, we are collecting the bottom of atmosphere reflectance after the atmospheric correction. So when we are correctly identifying the in the level 1C, the bottom, the top of atmosphere, then we are looking for the bottom atmospheric reflectance after its atmospheric correction. The very important idea, level 1C, top atmospheric reflectance, and the level 1, 2 is the bottom atmosphere reflections after atmospheric correction. The below level 2A is exactly the happening when we are purifying the atmospheric correction. So then we are having the bottom atmosphere's reflectance. So these are the data levels used by the European Space Agency, which is inspired by the NASA levels of data. Now, how Sentinel-2 data is processing level 0 and level 1A. We have seen produce our internal to payload data ground segment and are not available to normal users. Exactly, it's obvious because in the level 0 the data is the data is compressed of raw images. If you see, we have seen the raw image data, and the level 1A it was decompressed situated in the level 0. So this is not available to the end user. Sentinel-2 MSI data is systematically processed up to level 1C. Systematically, it's processed up to 1C. Then after the processing to the level 1C, it's really easy to process for the bottom of atmosphere. The visible difference between the level 1C and the level 1 2A. In the level 1A, it is the corrections of the atmosphere, top of atmospheric correction. After that, top of atmospheric corrections, we can find the bottom of atmospheric reflectance is mainly due to the atmospheric correction. It's no big difference. If we are having the level 1C data of the top of atmospheric correction, so we can easily find the bottom atmospheric correction. So correct after the bottom atmospheric correction, we can find the reflectance of bottom atmosphere or BOA. So this is how the data has been processed and the availability to the final users. So the data is exactly available to the users from the level 1C of the Sentinel-2. Now data compression. Satellites since are large, open hundreds of MB or several GB. So those data which are sensed by the satellites is a really huge data, It's in the hundreds of MBs or several gigabits or even terabytes. So compression reduce storage requirements. So that's why data compression is really important in the remote sensing due to saving the data, the storage. So compressions reduce the storage requirement as it's one of the important aspect of the hardware. So compression ratio is equals to the compressed size divided by the original size. So what is the compression size? If you divide by the original size, we can get the compression ratio. The key idea is the compressions modifies encodes or convert the bit structure of the data so that it takes a less storage space. We discussed the bit per depth, which is 2 to the power n. In that case, if we see the bit of the data we are collecting, it's really easy to give us the picture about the whole data size and after the compression, the size of the data, and we can easily find the compression ratio. So in the key idea, that's why they say the compression modifies or encodes or convert the bit structure of data so it takes a less storage space. Now we will see some certain types of the data compression, which is really helpful to understand. Like the types of the compressions, the start one is lossless, lossy, and near loss. Near lossless. The important one which we are using in the remote sensing, it's near lossless. Let's step by step discuss what is the lossless. Original data can be perfectly reconstructed. Example is like a zip. How much data we are having, it can be reconstructed as it is, how much it was or what was the original data. But in the lossy case, original data cannot be perfectly reconstructed, so there is a chances we can lose a little bit data in this case, which is not really important. In the near lossless, so we are having a controlled information of a loss. Like for the example of the JPEG 2000 is really famous of the type of compression for the remotely sensed data. Now, which one compressions we are using for the remote sensing data? That one is exactly the near lossless, because this compression is often useful because it is balancing the file size and control data quality. So we are having more control over what we need to laws or what is the size we need exactly and how much we need to reconstruct in the quality everything. So that's why it's really important. Near lossless. Near is lossless. It's not fully losing and it's not fully reconstructed. So it is like in the intermediate of between of lossless and the lossy. So that is why it is a hybrid type. Now it's one of the special storage format. It's called SAFE. So SAFE means Standard Archive Format for the Europe, and it is used by the European Space Agency ESA for the Sentinel products. So SAFE is based on the concept of OAIS, which is the Open Archival Information System. A Sentinel-2 SAFE products may include the image data, exactly what image data is like after reconstruction, when we are putting the grayscale or true colors, metadata and the XML metadata is important. We discussed already. It's information about the data, the quality indicators, auxiliary data, and preview images, granules, and tile folders, and the manifest.save file. So the key idea about the safe storage format, it is not just a single file format or extension like we know about the image formats like PNG or JPEG or something like that. It is a structured package containing the data in all supporting information. So it is a complete package which holds the all data and supporting information for the safe format, which is based on the concept of OAS, Open Archival Information System. So this is a really important format for the European Space Agency of the remote sensing data. So here we are having some of the common raster formats. The common for raster formats, we discussed that the raster format is basically used by the remotely sensed data in the optical remote sensing, which is really important. And it's in the ordinary, the pixel format of rows and columns. So famous formats are TIFF, GTIFF, ECW, GRID, IMG, SID. So from these, we have discussed some of them like TIFF. TIFF is exactly having some abbreviation. It is TIG, TIG image file format. It is the abbreviation of the TIFF, tag image file format. So it is a flexible and can store the compressed or uncompressed data. They can compress, they can store both of data types. Either it's compressed or uncompressed. It can store the discrete or the continuous information in the layers, pages, or tiles in the header tags, as the header tags can be saved because the format is the tag image file format. That's why they can save the tags also. Now the interesting and important format is that is GeoTIFF. And if you remember, we discussed that the GeoTIFF is a TIFF with a georeferencing information embedded or linked. When we were discussing the tiles or the formats, georeference, yeah, tiles and granules. In the tiles and the granules, we have discussed that is basically the tiles are user-oriented georeference products. So exactly the tiles are associated one of these formats of the GeoTIFF, which is holding the or embedding or link the data of the georeference data for the user. So this is exactly, that's why we said this is more user oriented for the final user, and the granules are the hardware oriented. We discussed the safe storage format. We were discussing some of the raster formats. So we discussed the TIFF format, and we discussed the GeoTIFF. The GeoTIFF is exactly the same like the TIFF, but the important thing is that they are embedding the georeferencing information for the end user. The another one is a TFW. This is, in my opinion, not a complete acronym to be explicitly right like in the TIFF, which is the tag image file format. So it is a TFW is a world file that gives the georeferencing parameters. So exactly this is more detailed file of the GeoTIFF, which we discussed, that is exactly helping as a georeferencing information for the final user. So this file TFW is exactly holding the georeferencing information, parameters such as the cell size, like the style size and the orientation, but it does not define the coordinate system itself. That's the important precaution or the warning to note it down. The coordinate system is not defined by the TFW format, and it's pre-encoded in the georeferencing parameters. Now we have the raster in the vector data. In the raster in the vector data, if we see, remote sensing data is naturally raster because sensors acquires data in a grid. We already discussed this, that the remote sensing data is usually or almost in the grid for the raster form, which acquires the data in the grid. We discussed the raster grid. It is in a rectangular format of the pixels holding a single value or multiple value, depends upon the bands, in the second or the third lecture. So now what is raster data and what is vector data? So the raster is based on the regular grid of cells or pixels. We already discussed this. And what is the benefit? It is it is good for the reflectance, elevation and height or altitude, temperature, the soil of the power hydrogen of the soil, continuous surface and spatial statistical analysis. So for these purposes, the raster data is very good. Vector data represent the features as a geometrical shapes like line or points or polygon. And this is good for the roads or parcels, buildings, administrative boundaries, and trees and all these. So this is the benefit of the vector data. Now we're looking for the rasters data pros and cons. They have some benefits, but also some cons. As we discussed, this is the simple metric structure, and it is in the form of the pixels and or cells. It's a powerful for the spatial statistical analysis. This is really important when we are mapping the spatial information. So raster data is really helping for the multiple analysis of like a covariance or semi-wiregram and semi-variance and multiple analysis of the spatial analysis. This is really helpful. Good for the continuous surface, as the land surface is continue. So it can represent the point, lines, polygon, and surface. So this has also this feature that they can represent the points, lines, and polygons and surfaces. and it's fast to overlays with the complex data set. So yeah, this is very fast for the complex data set. And raster disadvantages, that is the advantages we have discussed. It is special inaccuracies due to the cell size. We discussed that they have a certain cell size or pixels, so the special inaccuracies can cause this one in certain cases, because they have a fixed number in the pixel we discuss for starting from 0 to 255. It depends upon the bit depth, and it's a large storage requirement. Exactly, they need more storage in if even using the compressions, data compression, still they require more space. And loss of precision because real shapes are forced into a grid or cell. We discussed that they are using grids or cells, and it should be very forceful for that, and they are losing the precision. That's why this is the the third cons of the raster data. Although we discussed this is powerful for the spatial or statistical analysis, but they have some inaccuracies due to the cell size. Still we are using, but this is at the same time disadvantages also. Vector data and its formats, as we discussed, that the vector is good for the lines, points, and polygons, which is really good for the administrative boundaries, for the trees, for the parcels and roads. So now we are discussing the vector data and its formats. So vector data is exactly using X and Y to coordinates to represent the map features. So if we see the Google map, they are exactly using the vector data in the normal format, and that is exactly using X and Y to coordinate something, X, Y, and coordinates to map something on the film, to map something on the I mean to feature something on the map. This is the idea of the vector data, how they are working. The popular formats of the vector data is GML. GML is the geography markup language. KML is the keyhole markup language, and shapefile is ACD vector format. SDF is a spatial data file. So these are some of the famous formats of the vector data. And there is the key comparison. Raster is better for the continuous phenomena, as we say that the when we are taking a complete data take, so the complete data take is a continuous acquisition. So that's why we are using the raster data, and vector is better for the precise features and boundaries. So this is the one of the main differentiation of the vector in the raster data. So these are some of the famous GML, KML, and shapefile and SDF of the vector data, which is very commonly using in the vector data of the remote sensing. Really important concepts of the DEM, DSM, and DTM. DEM is the digital elevation model, and DSM is digital surface model, and DTM is the digital terrain model. So what is DEM, or digital elevation model? As from the word elevation means the altitude or height. So this is a generic term for the electronically stored 3D models earth surfaces. So this is, we can say that how the 3D model of the earth surface is stored. It is exactly the digital elevation model, and it is usually using the X and Y coordinates to feature something on the map like geographic coordinates. In the Z is exactly representing the elevation above referencing model. As we are seeing the stuff in the 3D, so they are having the third parameter of a Z, which is exactly representing its height or on the top view. So that's why when we are looking something on the top view, they are exactly representing its height or altitude. So this is exactly how we store the digital version of the Earth surfaces electronically using the three coordinates of the X and Y and Z, and Z is exactly representing the elevation above the referencing level. It is exactly as a reference level, we are looking to the height. So DSM is the digital surface model. Digital surface model is exactly the same if you see the picture. In these pictures, the above is DTM, digital terrain model, which is using for the administrative boundaries and all this stuff we discussed previously, the vector data. and all of them are using DTM, DSM, and DAM, the vector data. If you see the digital surface model, the things as comparisons to the DTM is much clear and visible, and it is exactly the digital versions. So the digital surface models includes all the features on the ground, starting from the building, trees, terrains, and objects. So this is exactly we are representing the digital surface model. The third one is digital terrain model. So digital terrain model is exactly discussing how the landforms are formed on the surface electronically or digitally represents an underlying terrain only. So they are only dealing with the terrains. A DTM may also include specific geographical elements such as river, ridge lines, and terrains structures. So that's why in comparisons to this picture of the DTM versus DSM, if we see the information in the DTM is much less in comparison to digital surface model, because they are more dealing with the geographical elements of the rivers, ridge lines, or the terrain structures. Important distinctions, the DSM includes the surface objects. They are only dealing with the surface objects of the land, but DTM is representing the bare terrain, mainly bare terrains of the geographical elements. So this is the DM, DSM, and DTM. Raster DM now in versus 10DM. These are two models we are discussing. So far we say the DM and DTM and DSM already. DM is exactly digital elevation model and DSM is the digital surface model, and the third one DTM was the digital terrain model. The raster DM versus 10 DM. 10 is exactly stands for the triangulated irregular network. A DM can be represented as a raster DM. Okay, it's not necessary to be vector, but also be possible to represent it as a raster DM, but in the regular grade of or the cells or the pixels. It is simpler and faster for processing and is less efficient in flat areas. Not ideal for the complex relief variation. So these are some of the advantages or disadvantages at the same time, or definition of the raster DM, which is in the form of the regular grade, but it's good for the fast processing and simpler, but less efficient in the flat areas where we are having the flat areas. So raster digital elevation will not work much better, and it's also not ideal for the complex relief variation also. So for the complex relief variation, then we are having another one, the 10DM, which is the 10 mean exactly triangulated irregular network. It's made of non-overlap triangles. It is exactly triangles on the map, but they are not overlapping each other. And it is based on the meaningful points of such as peaks, valleys, slope points, or slope changes. And it's more complex and slower because this is not overlapping, and this is using processing much data, so adapt better to local terrain complexity, where we are having the terrain complexity, so they can adopt very easily, and it's better for the natural features like watersheds. So this is a short and the quick difference of the 10 DM and raster DM. Now we are looking into the visualizations of the earth observation data. As we have seen so far, the data which is sensed by the satellites are not the images directly, they are numerical data sets. So images are created to help the humans interpret the data. To visualize the data, numerical values are translated into the gray colors, true colors, or the pixels. So very important idea, the value lies in the data. Still, the values which from which we are converting into the gray level or colors or the pixels, this is exactly lies in the data which we have observed, not in the image. Image is reconstructed from these values or numerical data sets. So this is how we are visualizing the earth observation data. This is more commonly observed, that what we are observing or sensing, it is directly the output of the images. No, it is exactly the numerical data sets we are collecting. Now we are discussing the matrix to image. The raw output of a scanning is a raster matrix. In the side pictures, we can see this is the you can see a raw output of a scanning. So when we are converting into the grayscale, so this is how we are making an image or picture from this. For the single band scalar data, values can be shown using the grayscale. We discussed already this before, how we are transforming the Earth observation into visualization. So this is the matrix converting to the image. So which represent by using of the values like a grayscale. So low values is like a dark. From the left side in the picture we can see, in the higher values means the bright. So where the values are lower, so they are representing the dark or gray something, and where the values are the high, so they are representing the bright. Each matrix cell becomes a visible pixel. Now this is becoming a pixel, so, and this is simple, but information is inefficient still. So how we need to complete our for the analysis purpose, and then we are visualizing the single band. The single band data can be displayed in a grayscale. The same we apply to matrix to the image. We are using the examples of a thermal data, panchromatic data. Panchromatic data is the all colors of a light sensitive to the electromagnetic spectrum. So infrared weather images, sometimes the scale may be inverted. For example, in the weather images, and exactly it is due to the weather reasons. That's why it is inverted. In the right side pictures, we can also see this. So this is how we are giving the our visualization to the single band. Multi-band visualization. In the multi-band visualization, each band can be displayed separately in the grayscale color. Again, we are giving these colors or true colors, but this spreads information across the multiple images. Multiple images mean like we have a multi-band data now. So into each band, we are giving them the gray scale color, so they can represent the information across the multiple images or acquisition. So better method is use the color composition. So we are using the color composition for the better understanding of the images, which is really good for the human icons. For colors, mainly use three primary colors of the red, green, blue. And exactly this is now more important. If you see the multi-band visualization in the picture, so this is multi-bands they are applying the grayscale colors. Still it's not much visible for the human eye, and the why it's more black and white is depends upon we have seen the raster, the matrix into the image. These values are transformed in the grayscale's value. The higher the value is, the more dark, sorry, the higher the value was yeah, the higher the value was, it is more bright, and the lower the value, it was a dark. So that's based on these. So where we are captured the electromagnetic waves very strongly, so over there it's much brighter, where it's weak, so it is a dark. But for the better understanding, still we need to apply the tri-stimulus theory, which is mainly discussing the RGB colors. And RGB is nothing red, green, blue, which is sensitive to the human icons. And these are these three colors. By mixing red, green, and blue, we are bringing multiple colors can be produced in the earth visualization. In the earth observation visualization, three selected bands can be assigned to RGB display channels. So these three colors are now assigned in the in the right side of the picture. We are seeing that the red, green, and blue are assigned, and that's why they are producing this kind of colorful images. See, this is applied like this color multiplied by this, plus this band is multiplied by the green, plus this acquisition or band multiplied by the red, and is the output. That's what we are looking at. It's much more sensitive the human eyes. So this is exactly the tri-stimulus theory discussing about. Now the true color in false colors comes into the picture. We have already discussed the false colors before this also, but let's quickly take a look into the true colors and false colors again. The true colors is exactly we discussed, that is the images assigns visible bands to matching the RGB channels. Like the red band is the red channel, and the green band is the green channel, and the blue band is the blue channel. So it looks close to human vision. The human vision can really easily identify these colors and its combinations. What is exactly the false colors and what they are representing? False colors doesn't mean a fake color, but false colors is using other bands combination than the red and green and blue, and they are for the sake of to reveal the characteristic of the target, often including infrared. So we are using the electromagnetic spectrum, electromagnetic, sorry for the visible word, electromagnetic spectrum, possible light of the infrared to reveal the characteristic of the target object. Like for example, we are having near infrared. So near infrared is the red channel in the infrared. In this case, if we see, the vegetation is mainly expressed by the near infrared, highly visible or highly reflected. So this is exactly the red channel. In the red, near infrared, if we see, it is exactly the green channel, and the green is exactly a blue channel in the near infrared. So this makes vegetations appear bright. As already I said, this makes the vegetation appear bright red and helps highlighted lane cover differences. And this is why we are using the false colors to differentiate the multiple features of the surface, multiple objects. Here we can see in the left and the right side pictures, the middle one is the true colors using, but in the right and the left they are targeting a specific thing in the targeted area. That's why we are using the infrared or the false colors to identify these stuff. So that's the makes vegetation appear very bright and red, and it helps to highlight the land cover differences. Pseudo colors are the another colors we are discussing for the Earth observation visualization. And the pseudo colors means you can call them, they are not representing any real colors. So pseudo color means used for the scalar or the single band data. So they are applying to a single band data. If you can see in the right side, it is especially using for the multiple purposes, like it is useful because the human often perceive more details and color than the grayscale. So directly in the grayscale, it is not really easy to understand, but colorful is more meaningful for the human eyes. Uh, Example of the pseudo colors, if we see ocean temperature map, when we are identifying the ocean temperature map, so we are using the pseudo colors. It's really easy in helping the human eye that can be identified instead of the grayscale color. Exactly, these are not the colors which is directly visible to the human's eyes, but we are trying to or the scientist tries to make these colors again visible to the human eye with the certain targets, or the way certain characteristics they would like to see in the target or the land surface. And like we would like to make the elevation map, which is the height or the altitude map, and the thermal map, it is exactly discussing the temperature of the land or the objects on the earth. So for this stuff we are using the pseudo colors. It is used basically for the single band, and it does not represent any real colors like the RGBs, but we can convert them. Uh, and if you see in the right side, this is an example of a pseudo color versus the grayscale representation. So this is exactly the representation of the grayscale. The right hand side is the grayscale, but this grayscale is then converted into the pseudo colors. Now the pseudo color is having colors, but they are representing in not exactly the real colors which we are looking for. If you see, this is the totally multiple combination of stuff. Even there is no certain color in this one. Not note that how much more details perceivable in the color case. So it depends upon the application, how much it can be perceived in that one. Last one is the other color spaces. So far we have discussed multiples like for how we are going from the matrix to image. Then we discussed the single band color, and then we have seen the multi-band color. If we see the single band visualizations and multiple band visualization, then we have seen the RGB and tri-stimulus, the true colors and false colors, pseudo colors. But along from these, we have more color spaces also, like HSI, HSB, HCl, HSV, CMYK, UV, CI. In the Earth visualization, the RGB and HSIs are the most widely used. So RGB, as we discussed already, but one of them is also really famous for the remotely sensed data Earth observation visualization, which is common HCI. So this is also one of the there. This is basically hexa decimal something. They have some abbreviation of this word. So they are using the uh, a certain type of code for the colors, which they are representing a certain color. So it is HCIs, and these two RGB and HCI is using mostly in the remote sensing Earth observation visualization. So HCI meaning is here already given. H is a hue, saturation, intensity. One of them I was talking about that's different, not this one. Hexadecimal colors, that's also representing with a certain code. It is exactly the hue, saturation, and intensity. It is called HCI. So HCI and RGBs are the most commonly used in the remote sensing data color spaces. So this is all about the data formats and the visualization, and this was the last lecture in the remote sensing products. We discussed in the remote sensing products the remotely sensed data and the data formats and visualization. In the next lecture, which is a totally new glance, it is about the basic analysis. We are starting with the data corrections, and then we will be discussing the basic analysis, and that glance will be finished. And the last glance is about the advanced data, advanced analysis and its application. So we will having two more lectures in that one. So we completed the fifth lecture. See you in the next lecture. Bye for now.